Now let us take up the method of preparation for ethers. There are two methods. One is intermolecular dehydration of alcohol and another is Williamson synthesis. Intermolecular dehydration, as the name suggests, a molecule of water being taken away from two molecules of ether and two molecules of alcohol, and it is acid catalyzed reaction. So we write the reaction ROH plus HOR. It is catalyzed by acid and heated at low temperature, and we get ROR and H2O. This method is suitable only for preparation of symmetrical ether. No unsymmetrical ether can be prepared by this method. So we have taken the example methanol, two molecules of methanol in presence of proton and heated to 414 Kelvin gives you dimethyl ether or methoxymethane. Now we need to do the mechanism for this. So step 1 will be protonation of alcohol. Remember, proton means H plus and it is behaving as a catalyst. Now the speciality of a catalyst is after the reaction is over, the catalyst has to be made free. So here methanol is attacking the proton and it is forming an oxonium ion. Oxygen bearing positive charge, we call it oxonium ion. Step 2, this another alcohol molecule will behave as a nucleophile and will attack this particular oxonium ion at the carbon attached to oxonium ion. So you can see here how it is attacking and the water is becoming free. So here this has attacked the carbon and the water is made free. So we get another oxonium ion here together with water. Now we see we have almost got the product, but only this H is extra. So we have to get rid of this H. So step 3, we have to do deprotonation to release the catalyst which was used in step 1. So that's how we get a symmetrical ether by dehydration, intermolecular dehydration of alcohol. The second method is Williamson synthesis, a very important method, because this method is a general method because it is capable of giving you both symmetrical and unsymmetrical ether. Now when haloalkanes react with sodium alkoxide or potassium alkoxide to form ether, it mostly undergo SN2 mechanism. Both symmetrical and unsymmetrical ethers can be prepared by this method. So I have taken here Rx, which is haloalkane, sodium alkoxide, which is an alkoxide obtained from alcohol. Both the compounds can be obtained from alcohol, and we get an unsymmetrical ether. Now usually the smaller alkyl group R comes from haloalkane and bigger alkyl group alkoxy comes from alkoxide. So when you prepare an unsymmetrical ether, you can see the CH3 being smaller has to be obtained from haloalkane, and ethyl being bigger in comparison will be obtained from alkoxide. That is the speciality of Williamson synthesis. Now to find out the starting material for an unsymmetrical ether, normally what we do, because in the exam they never give you to complete a reaction, hardly will find the giving question to complete a reaction. Normally they give you the product and ask you to find out the starting material. So for that what you do, first you write down the product given to you, then above oxygen you write sodium, okay, and third step, to the less bulky group you put the halogen as it is put here, then you break the bond. From where we got this sodium halide? Because you can see the byproduct formed is sodium halide. So if we add this sodium halide here, we will get the starting material. So this way when we proceed, we will never make mistake. So we can apply one example. You can see here when this particular technique is applied to an example, you have been asked to prepare methyl phenyl ether, that means anisole. So first we write down the structure, then above O we write Na, and compared to these two, this is definitely smaller, so we put the halogen on the smaller side and then cut, and that's how we get the starting material sodium phenoxide and bromomethane. So that's how we have to work it out for the Williamson synthesis. Thank you.